Hello, part of my little short set of explanations and connections of explanations of probability ideas and statistics. So let's have a look at the binomial distribution and use a quick example here. And we roll a dice 5 times. What's the probability of getting 4 6s? Well, we know that the probability of getting a 6 we could work out is 1 in 6, and therefore the probability of not getting a 6 is 5 in 6, and we could use a probability diagram tree here, and is our 5 throws of the dice, and with green here we've tracked out that worked out our probabilities, haven't we? We've got a 1 6 here times another 1 6 times another 1 6 times another 1 6, and then finally a 5 6. And then, as we can see with the green lines, we've got 5 different routes, because it doesn't matter to us whether the non-6 is the first, second, third, fourth, or fifth one. So ultimately, before we know where we are, we've worked out our probability. We've got our 5 routes, and we've got our 1 6 to the power 4, because we got 4 6s, and we've got our 5 6 because we have one non-6. Here we go. So that's pretty straightforward. Now, we know quite a lot about binomial from C2, don't we? And if we generalized it here with 2 values, P and Q, and we do it to the power 5, we get the expansion there. And lo and behold, look, here's the same term. There's 5 6, 5 is the multiplier rather. Then we've got our 1 6 here to the power 4, so that would be our P value, and 5 6 to the power 1, that's our Q value. And lo and behold, what do we know about P plus Q? Well, one's on 6 and the other one's 5 6, so it adds up to 1. So our life becomes very easy and consistent, doesn't it? Because P plus Q to the power 5 is also going to be 1. Well, where have we seen this structure before? We've seen it in Pascal's triangle, haven't we? Where it builds up with our 1, and then our 1, 1, and then our 1, 2, 1, and we did it by adding them up, didn't we? Yeah. And if you think about it, that fits in with our multiplier here of 5, because there's loads of ways we can get to the 5. Well, we could have gone this route here, 1 1 1, or we could have gone that route here with our 1 1 1 and then non-1. Could have gone that way or that way or that way or that way, and lo and behold, how many routes have we got of getting there? Well, there's 5 of them. And if we did the same thing elsewhere, we'd have 10 if we were going down choosing 2, wouldn't we? So as we know, the Pascal's triangle numbers fit exactly with our n choose r. And why is it going to fit with our n choose r? Because, well, here we've got 5 choose 1, and the choosing, if you remember, we don't care about the order, do we? Doesn't matter whether you choose it first or fifth. So that all fits together, doesn't it? And so as a result, we get our very nice simple probability idea. One other thing just to pick up is that the P is unchanged all the way through, isn't it? We're using the same probability all the way as our P value at 1 6. And we know how many trials we're running. Here it's 5 trials, yeah? So our life is pretty straightforward as to why it should all come together into this equation, where n is the number of trials, r is our number of successes, P is our probability of success, and Q is going to be our complementary probability, i.e. the probability of failure. It's going to be 1 minus P. Intuitively, we can see that if we just went back to our example up here, that our expected value is going to be NP, because here we had 5 trials, didn't we? And each one is got a probability of success of a 6, so overall we would expect on average 5 6 of a 5 6 of a 6. So there we are over that lot. That makes sense, doesn't it? So there's our NP value. And one that's less obvious we can derive elsewhere is that the variance is going to be NP times Q, but there's a fairly straightforward calculation for how that is. So there we are. That's why it all fits together. That's why we can take a multi-trial independent with the same probability, and we can apply binomial to it and use our binomial formulae. Have fun.